Welcome everyone, welcome to the course of Digital Signal Processing. Today we will continue our chapter number 2 and lecture number 3. In previous two lectures we have talked about discrete time signals, discrete time systems, we have discussed the properties of discrete time systems, and we finally talked about convolution and LTI system. In today's lecture we will look into convolution further, and then we will talk about the properties of LTI system. So let's get started with today's topic. So in this slide we will compute the convolution sum of two signals that are given to you. So you can see that we have h of n, there is a response, and this response is between 0 and n minus 1. So this is finite impulse response, and it depends upon the value of n, that how many samples are going to be in h of n. Then we have this x of n signal, which is exponential, and exponential on the right side only because of the u of n. So we have to find out the convolution sum of these two signals, x of n, h of n. So for that we need to obtain x of k first and h of n minus k. So clearly we can see from these two signals that output will be 0 for n less than 0, because there will be no overlap, because this signal starts from 0 and goes towards n minus 1. Say n is equal to 5. So this signal starts from 0 and goes towards 4. So only on the positive side, and this signal also goes on the positive side. For example, if I draw h of n will be 0, 1, 2, and let's say this is n is equal to 4, so this will be 3. So this is h of n, and if I draw a raised power n u of n, it is going to be this signal 1, then increasing, and it will increase, and it will go towards infinity. So if I multiply these for n less than 0, output will be 0. Okay, so now we have overlapping in the region. So this is the formula. If I multiply x of k with h of n minus k, because this is only 1 and this signal is a raised power n. So if I write x of k, so the multiplication of two sequences will be a raised power k, because we are replacing this independent variable n with k. So we have to obtain x of k first of all, and then we have to obtain h of n minus k. So h of n is basically 1, and this is a raised power n u of n. So the multiplication of these two will be simply a raised power k. Okay, so now between 0 and n minus 1, we know that there will be overlapping from 0 to n minus 1. So this is 0 to n minus 1. If we multiply, the summation will start from 0, because the first point that will convolve will be 0 to n minus 1. So we have this interval 0 to n. Okay, and it depends like where we are going to end this convolution. So 0 to n minus 1, this is our first interval. So let's move on to next slide. So this is x of k. So this signal, you see, this is decreasing. So okay, so previously I have drawn x of k like this. Sorry, x of k like this. So it will be increasing if a is greater than 1. If a is less than 1, so it will be a decreasing sequence. So this is our x of k, and this is h of, so h of n was like this, 0 up till n minus 1. So if this is h of n, h of minus k will be like this, 0 like this, 0 minus n minus 1. Okay, so if I write h of n minus k, it is going to be like this, 0 point will be shifted to n, then we have many samples, and then finally point will be h of minus n minus 1. So this is shifted, this is shifted. So now if I convolve these, you can see that we are not going to move x of k, we are going to shift and slide this h of n minus k. And what values we can change? We can change n. So we know that if I move n to this point right side and this point is still on the left side, there will be a convolution. So we can say that if n is greater than 0 and n is less than n minus 1, so one overlapping is this is known as partial overlapping. Okay, this is known as partial overlapping. You know that one signal is finite and other signal is infinite. So in that case we have first of all one interval that is no overlapping, which we have already discussed, and then we will have partial overlapping. So this is partial overlapping. Here we have full overlapping. You see that if I say that n minus n, this point is greater than 0, this point is greater than 0, okay, then we will have full overlapping. So you can see that we have full overlapping. All these samples are multiplying with these samples. So this is full overlapping. Okay. So here in this particular example, we will have only two intervals, that is either no overlapping, partial overlapping, and full. So this is partial, this is full, and this is the output of combining this partial and this full. So let's move on to next slide and see the equations. So before I start, you must need to know what's the formula of geometric series. So if this is exponential sequence and alpha here is less than 1, and we want to add from n1 to n2, then this formula is of geometric series sum. So argument, that is alpha, first term, when you start summation, first term is n1, and n1 can be any number that is less than n2, minus alpha last term, that is alpha is for n2 plus 1, divide by 1 minus ratio, that is second term divided by first term, so the ratio will be alpha. So our first interval, so if we apply the formula of this geometric series to equation 2.55, we know that our first interval was that k starts from 0 and goes toward n. So that was our first convolution interval. Like obviously one signal is starting from 0. It is like 0 before 0. There are no samples at -1, -2. So obviously the convolution will start from 0 and goes towards n. And if this is the first convolution interval, and that is of partial convolution, which I have already told you in previous slide. So the formula of this geometric series will be first term, that will be a raised power 0, minus last term, that is a raised power n plus 1, and ratio will be 1 minus a. So this will become 1 minus a raised power n plus 1 divided by 1 minus a. So this is the same thing, and the limit of n is greater than 0. So n is greater than 0. So if I shift n greater than 0 and n is less than n minus 1, so there will be partial overlapping. Okay, you got this point? So let me wrap this out and let's move on to next interval. The next interval is of, so finally 2.10. If you see the second figure shows two sequences. In that sequence we saw that there is full overlapping. Okay, so n minus, so we have n minus 1. This was our 1 point. Okay, so if I simplify, this will become n minus n plus 1. So when 0 is less than this, okay, when 0 is less than this, or we can say that n minus 1 is less than n. So in that particular case, obviously we have to define limits for k. So this is the point when this n minus 1 becomes greater than 0. Okay, we have seen that this point was n, this point was n, and this point was n minus 1. So when this point becomes greater than 0, it means that we will have full overlapping. So in that particular case, if we multiply these two signals, we will have a raised power k, the same thing, but the limits get changed here. Now k should be greater than n, k should be less than n, and k should be greater than this thing. So the limit will become k is equal to n minus 1 starting from this point. So from this point the convolution will start and the convolution will go towards n. Okay, so this is full overlapping, and n can be any number. Okay, so if I expand this, so this is again finite sum starting from some specific values, So first term a raised power n minus n plus 1 minus a raised power last term n plus 1 divided by 1 minus a. So if you simplify this, you know that we can take this term common and this will be n. So one output is this, the second output is this. This is for full overlapping, this is for partial overlapping, and before that we have no overlapping. So are the three intervals. For n less than 0, the output is 0. Okay. For n between 0 and n minus 1, we have this. And when n minus 1 is less than n, this is simply the same thing, that n minus 1 should be greater than 0. So if you simplify this, it will become n minus 1 less than n. So same thing. So this is the overall output. Now you can draw this by giving values to n, small n. So for example, if capital N is equal to 5, this will start from 0 and we have to give 0 to 4 values to n, and this will be like 4 less than n. Okay, so you have seen that in that particular convolution we have one signal that was finite and the other was infinite. So we have only 3 intervals. What if we have 2 finite signals? If we have 2 finite signals, keep in mind we will have one interval in which we have no overlapping. So no overlapping if both the signals are finite. Then we will have partial overlapping, then we will have full overlapping, then we have partial overlapping, and then finally we have no overlapping. So starting from left, move towards left. Okay, sorry, move towards left. Then move towards right slowly. So a point will come when you will have full overlapping, and then a point will come when you will have no overlapping. So first move on the left, then start to move on the right, and it's just like your one hand is still and the other hand is moving. So when your one hand become on top of the second hand, it means that we have full overlapping, and when the second hand is cutting partially the first hand, it means we have partial overlapping. So there are many ways of computing the convolution. For example, you can also compute the convolution by simply multiplying two sequences. Let me show you how you can do that. So if you have finite length sequences, there are many ways. The one we did was graphical method. For example, we have x of n is equal to, let's say we have sequence 1, 2, 3, and this point corresponds to 0, and h of n is equal to 4, 5, and this corresponds to 0. So we can draw this sequence. This is just an example. You can have any sequence of finite length. Maybe x of n can have 10 samples and h of n can have 15 samples. I'm just doing it because I have limited space over here. So 1, 2, 3, 1, 2, 3, and this is 0, and this is x of n. Okay, and h of n is 0, 1, this is h of n, and this is 4, 5. So I know that if I convolve these, this 0 will multiply with 0 and the output will be 4. So what I have to do, I have to write this sequentially 1, 2, 3, and I will write 4 and 5 here. Then I will simply multiply. I know that this is x, this is h. I will simply multiply these two. I know that 5 multiplied by 3 is 15, 10, and this is 5. And then I have to make a space. 4 multiplied by 3, 12. 4 multiplied by 8, 2 is 8. And then I will have 4 multiplied by 1, that is 4. So if I add them, this will become 4, 13, 22 and 15. So I know that 0 multiplied by 0 was 4. So this is 0 at 0 index, that is at 1, this is at 2, and this is at 3. So the output y of n will be, this is simple multiplication method. So this is multiplication and this is kind of a shifting, and then we have addition. So all of the operations are performed. So it will be like output will be 4, 13, 22 and then 15. This is 15, this is 22, this is 13 and this is 4. Please draw them clearly. We usually put hollow circle on top of these. So this is 0, 1, 2, 3. So I can also tell what will be the length of convolution. The length of convolution, keep in mind for finite sequences, length of convolution, it is m plus n minus 1. So m is the length of x. How many samples are there? 1, 2, 3. So 3 plus how many samples are in H2? Minus 1. This will become what? 5 minus this will be 4. So you can see we have 4 samples at the output, 0, 1, 2, 3. Okay. And we can also find out the starting point of the convolution. Starting point of the convolution is minimum of x plus minimum of h. So the convolution will start from here. So the minimum of h is 0 and x is 0. So convolution will start from 0 and goes towards maximum of h, maximum of x plus maximum of h. So if I add these, this was maximum was, so this was like 1, 2, so 2 plus 1, 3. So it will goes towards 3. So the starting point was 0 and the ending point was 3. So I told you in this slide that we can find out the overall length of convolution, that is total sample in x plus total sample in response, that is h, is equal to length of convolution, and you have to subtract 1. So m plus n minus 1, and if you add minimums you will get the starting point, that is 0 of the convolution, and if you add the end we will have the ending point. I know that it's not easy to explain the convolution here on this slide, but I hope that you will get maximum out of what I've told you. Okay, so let's move on to next slide and see what we have out there. So in this slide we will discuss the properties of linear time invariant system. We know that for linear time invariant system we have convolution sum for discrete signals. Okay, so here we are going to discuss the properties of convolution. So the properties of convolution or properties of LTI system are same. So first property is this property, which is known as commutative property. So it doesn't matter if you convolve x of n with h of n or you convolve h of n with x of n. So here you have to flip and shift this signal. Here you have to shift and flip this signal. So it doesn't matter, the output will remain same. So this is commutative property, that you can switch the positions of these two. So here is the proof of shifting all these. So for example, we have shift and flip in x. So here we have x minus m, n minus m, and then we have h of n, and we have shown that this is equal to this thing. So how? If I take like so this can be shown by applying a substitution of variables to equation 2.52 specifically with m is equal to n minus k. So we know that our typical formula of convolution, I can write here, I have very limited space. So x of k h of n minus k. Okay, and k is equal to minus infinity to infinity. So it says that if I take n minus k is equal to m, it means that n minus k is equal to m. If I take this thing, n minus k is equal to m, so this will become h of m, and this will become x of n minus m. So this thing. So from here I got this thing. This is equivalent to writing this thing. Okay, it means that if I simply write x h of m and we have x of n minus m, these are both same things. Okay, so we just did some substitution. So in original formula, if you put n minus k, you will get this thing. Okay, so we it proves that both are equal. It means that we have to shift and flip x. We have to shift and flip x. We have to keep response steady. So here we have just rearranged them, writing h of m before x of n minus m. So this is basically h of n convolving to x of n, because before this it was x of n convolving to h of m. So after convolution sign, whatever signal is there, we will shift and flip that signal. So before we were shifting and flipping h, now we are shifting and flipping x. So this is first property, that is commutative property. And the next property is distributive property. It means that convolution can be distributed. So for example, if you have two systems, you have one input and that input needs to be passed from two systems. So for example, we have this kind of a arrangement. Sorry, I can rub this and I can redraw it for you. For example, we have this kind of situation. This is first system, this is second system, and then we have output here. So what we can do, we can add this and this. So it is easier to convolve x with this one and this one. So here you can see we are adding, because addition is easier. So we are adding these two, and whatever the overall response, we are convolving this with x. The other way is that I can convolve x with h1 and then I can convolve x with h2. So this is distributed, like distributing the input on two impulse responses. Okay, so distributing the input on two impulse responses. So this is distributive property. You can also do this thing. Now this is for parallel connections. Okay, this is for parallel connection. And in cascade connection, this is cascade. In cascade connection, the response will multi-convolve. Okay, so for cascade, I mean, for example, this is one response, then we have second response, and then, for example, this input needs to go from this system, then this system. Okay, so the overall impulse response will be first solving these two. So I have to convolve these two and then I have to convolve the input with response. So this is for parallel system and this is for cascade or series system. Okay, so let's move on to next slide and see what we have there. So you can see here three linear time invariant system with identical. So the impulse response of all these are equal. So this is first impulse response, this is second impulse response, and this is input. So according to the commutative property, we can switch. It doesn't matter if we convolve x with h2 and then convolve with h1. And what if we just convolve these two first? So here we have these two convolve and we have response. So the output will be same. Output will be same of all these three. And this is only possible because we know that h1, h2 are linear and time invariant. These systems are linear and time invariant. Only then we can like reorder them. So all these are example of cascade. This is cascade system, series, and then we have solve these two series. So let's move on to next slide. Here we have parallel connections. Okay, so this is kind of a distributive property. One system, two system. So either what I can do, I can convolve this with this, and I can convolve this with this, and then I can finally add them. Or other way is that simply add two impulse responses, add these two, and then whatever the net impulse response is, convolve this with x of n. So this is parallel combination of LTI time invariant system and equivalent system. So this is an equivalent system. Okay, in parallel connection, the system have the same input and their outputs are summed to produce the overall output. So the impulse response is added here. Okay, let's move on to the next slide. So in addition to the distributive property, associative property and commutative property, I forgot to mention that cascade is basically associative. Okay, cascade is basically associative. There are a number of other properties as well. The other property of linear and time invariant system is whether the system is stable or not. So we know that if the system is stable, the impulse response, that is h of k or h of n, must need to be what? It must need to be absolutely summable. So we have to sum the impulse response, that is starting from minus infinity to infinity. Whatever the values of impulse response, we are going to add the amplitudes. Here we are going to add the amplitude. So if it becomes less than infinity, it means that our impulse response is stable. Okay, so we have to sum the impulse response. So there is a simple proof, like this is the formula of convolution. Everybody knows that h of k x of n minus k. We have to take mod on both sides. So if I take mod on both sides and then I distribute mod, so obviously like 2 minus 5 plus 3, or 6, sorry, 6 plus 2 is 8, 8 minus 5 is 3, the output will be 3. However, if I take individual mod, minus 5 plus 6, the output will be 11 plus 2, there is 13. So obviously 3 is less than 13, so here we have distributed the magnitude, this absolute, on x of h of k and x of n minus k. So accordingly we can say that we know that if input is bounded, x of n is bounded, it means that this thing is bounded. If input is bounded and input is less than some value b of x, then according to the formula, output will be less than b of x. So only thing I need to care about is that, so the formula that left behind is this. So this is the same thing which is here, that input is bounded. The only thing that we need to care about is that the impulse response is bounded. So if impulse response is less than infinity, so the system will be stable. So let me recap it for you. For a system to be stable, or the impulse response to be stable, the impulse response must need to be absolutely stable, summable, sorry. So we have two items in convolution formula. One is response and one is input. We already know that if input is bounded, output will be bounded. Okay, so x of n is bounded. It means that x of n is less than b of x. So we can substitute b of x in place of x of n minus k, which is just a shifted version. So according to this formula, this is okay. The only thing need to care about is that impulse response is less than infinity. So this is the condition for stability of LTI system. And next we will look into the causality of LTI system. So LTI system will be causal if impulse response is 0 for n less than 0. It means that if impulse response is only defined for positive side, okay, it is 0 here, so the impulse response will be causal. What about this impulse response? This impulse response is not causal because it is defined at -2 and -1. So if the impulse response is 0 at n less than 0, this is causal impulse response. Okay, we can say the impulse response of the system is causal, so it must not be defined for negative numbers. Okay. So here we have examples of few impulse responses. So this is the ideal delay system. So all you need to do, we know that the ideal delay system is defined as x of y of n is equal to x of n minus nd. All you need to do for finding out the impulse response, you need to replace the input with delta function or impulse. So the output will be response. So this is the impulse response. Secondly, we have seen moving average system. So in moving average system, we have replaced the input with delta function, and we know that this delta function will be 1 in this interval between m1 to m minus 1. We know that this will be 1. Why this will be 1? Because delta impulses are shifting. So we can write this from -1 to minus m1 to m2. The function is only this, and other than this it is 0. Likewise, for accumulator system, we know this is our accumulator system. Y of n is equal to summation x of k. K starts from minus infinity and goes towards n. So here we have to replace this x of k with delta of k, and if we add them, what will happen? If, for example, if I add them, so if this is the input to the accumulator system, so the output of accumulator system be 1 1 1 1, because it's going to add previous, so there is only 1, so the output will be this. So we can say that the output will be 1 for n greater than 0. Okay, so I can simply show it to you. Delta of k is equal to minus infinity to n. So you know that delta impulse will give you 0. Delta impulse will give you 0 as long as k is negative. If k is -1, it will be 0. K is -2, it will be 0. It will first produce its output at k is equal to 0. So at 0 this will become 1. Then at when we go to when n become 1, so we will have delta of 0, delta of 1. So obviously this is 0, but we have already 1 here. Then we go to 2, we will have delta of 2, delta of 0 1 2. So this is 1, so this will always remain 1, so we'll have 1 on the positive side. So this will become u of n. So we know that if I give impulse to accumulator system, its response will be unit step. Its response will be unit step. And this is what? This is already told you, this is forward difference system. Forward difference system is advanced sample minus current sample. This is system y of n. So if you replace this with delta and with this delta, we will have this. And you can also draw this. How you can draw this? If I need to draw this impulse response, this is 1 at -1, and then at 0 this is -1. So this is delta of n plus 1, and this is delta of n. Okay, so let's move on to next slide. This is, again you can see here, this is our backward system. So current minus previous. You can also draw this. And here we are talking about the stability of the impulse response. So if I talk about the stability of accumulator system, we know that the impulse response of accumulator system is u of n. So if I simply sum them, the accumulator system, however, is unstable. Okay, because I cannot add unit step. Okay, so here I want to tell you about two things. One is FIR and the other one is infinite impulse response. If there are finite samples in the impulse response, it will be known as finite impulse response system. If we have infinite samples, it will be known as infinite impulse response system. For example, this. Obviously, if the impulse response of system is a raised power n, we know that this is infinite because we can have any value of n. However, if a magnitude is less than 1, if a magnitude is less than 1, okay, then we can use the geometric formula. So this is infinite series starting from 0 and goes towards infinity. So the formula for this will be first term a raised power 0 will be 1 divided by 1 minus ratio. So this is infinite series, but the sum will be less than infinity. You can check it yourself. For example, the value of a is 0.5. The value of a is 0.5 and I sum it from 0 to infinity. So as per formula, because if the power of a will, obviously a is 0.5, so the power will be 0, 1, 2, 3. So when the power will increase, the number will automatically decrease. 0.5 raised to power 100 will be a very small thing. So we can use this formula, first term divided by 1 minus ratio. Okay, this is the infinite series formula. So 1 minus 2, we know that, sorry, 1 minus 0.5. So 1 divided by 0.5, this will become 2. So if I add this a raised to power n from 0 to infinity, the overall sum will be 2. So here you are told about finite impulse response and infinite impulse response. So here you can see the impulse response. This impulse response, if you draw this is infinite. This will start from 0 and goes toward infinity. So this is infinite impulse response. Here the finite impulse response, this is finite impulse response because these are just two samples. At 0 it is 1 and at n minus 1 it is minus 1. Okay, so this is finite impulse response, this is infinite. And here we are talking about that for ideal delay. I can read it for you. For ideal delay, moving average, forward difference, backward difference, it is clear that if I sum this, the impulse response has only finite number of non-zero sample. So only finite number of non-zero, two samples here. Such systems are called finite duration impulse response. So where the samples are infinite, it will known as infinite impulse response. Okay, now the accumulator system impulse response is infinite because I cannot sum the impulse. I cannot sum this. H of n is equal to u of n. Can you sum this? No, I cannot sum this because u of n starts from 0 and goes towards infinity. So the sum will be 0. Okay, sum will be infinity. So that was about finite impulse response and infinite impulse response, or you can say finite duration or infinite duration. So in this slide we will talk about the concept of convolution. So for example, this is our system which is ideal delay system, and the impulse response of this system, you already know that you just have to replace the input with delta of n minus nd. So we know that if the impulse response is this and I convolve this x of n with this, what will happen? This is equivalent to delta of n minus nt. Which property is this? I just told you this property is commutative property. So if you convolve x of n with delta of n minus t, you will get x of n minus t. So output will be this. Okay, there is convolution of shifted impulse sequence with any x of n is easily evaluated by simply shifting x of n by displacement. So whatever the signal here is x of n, if you convolve this with shifted impulse, the input will be shifted by that number. Okay, so this is only applicable with again LTI system. Okay, let's move on to. So here you have forward difference and followed by one sample delay. So forward one sample delay is delta of n minus 1, Forward difference is delta of n plus 1 minus delta of n. It means advanced sample minus previous sample. Okay, then we have one sample delay convolving with forward difference. Okay, and then we have backward difference. It means current minus previous sample. So all these are equivalent. The output of all these are equivalent. How? If I convolve delta of n minus 1, n plus 1 with delta of n minus 1, it means that I want to give a delay in delta of n plus 1. So the delay in n plus 1 will be delta of n, and the delay in delta of n will be delta of n minus 1. So this is this thing. Now again, delta of n minus 1 convolving with delta of n plus 1. It means I want to advance delta of n minus 1. So advance means delta of n. Then if I convolve this with this, it means that what I have to do, I want to delay delta of n minus 1. So all these are equivalent. Equivalent system found by using commutative property. So this is commutative. Okay. So you can solve it yourself. All you need to do, you must need to know the equation. The equation of forward difference is what? I have already told you, advanced sample minus previous sample. So if you need to find out the impulse response, you just have to replace delta x with so this is the impulse response of forward difference. Okay, so let's move on to next slide. So here we have another cascaded system. This is accumulator system, and we know the impulse response of accumulator system is unit step. Now we have backward system. We know the impulse response of backward system. So if I convolve u of n with simple impulse, if we have one impulse and I convolve this with unit step, what will you get? It means that this impulse will multiply with this one, then we shift this, multiply with this one, so it will become u of n. Okay, and what if I convolve u of n with delta of n minus 1? It means that this signal, according to the property, this signal will become delay. So we are subtracting u of n with u of n minus 1. It means that we have this thing. This is u of n starting from 0 and goes toward infinity. And we are subtracting it from what? We are subtracting it for one shifted. So what will happen? This will cancel with this one. Only 0 sample will be left, which is delta of n. So this type of system is known as identity system. So it means that if accumulator, what does accumulator do? It adds previous and current values, whereas the backward difference, it subtracts. So ultimately both the systems are, what they are doing, they are cancelling the effect of each other. So the overall response is delta of n. It means that whatever at the input will be the output. So these two systems are actually cancelling out each other. So that's why whatever as the input will become at the output. So we know that if this is h of n, this is the opposite. This is inverse. Or if this is inverse, this is h of n. So if opposite impulse responses are convolved, the output will be delta of n. So if you convolve x of n with delta of n, what will be the output? According to the formula, the output will be x of n. So an accumulator in cascade with backward difference, since the backward difference is the inverse of the accumulator, the cascade combination is equivalent to identity system. This is identity system. Okay, input pass through system output, and then this output pass through the system, it will again become input. Okay, so we will have identity system here. Let's move on to next slide. So here we will talk about another important class of LTI system. This is another important class of LTI system, and this is very important to analyze, understand, because when we are going to design filters and when we are going to do the Z transform, this equation will be widely used. So all you need to remember is that when there is scaling at the output, there is scaling at the input, or you can say when there is scaling at the input, we have scaling at the output. And please memorize or remember that these are standard coefficients. These are standard coefficients. Like in most of the books, we will use B coefficients for input and A coefficients for output. So if there is scaling at the input, there will be scaling at the output. If there is delay in the input, there will be delay in the output. There is addition at the input, there will be addition at the output. So here the order of the input is M and the order of the output is M. So this equation is very simple. So you must need to understand sum of all the inputs is equal to sum of all the outputs. So there are three things. Let me again recap it for you. Scaling, there is Bm at the input and Ak at the output. X of n minus m at the input delay, and y of n minus k is the delay of output terms. And then the order of the delays, there is at input is m and the output is n. So this is linear constant coefficient difference equation. Why we say this is linear? Constant, these are constant. These are constant coefficients, okay, A, K or Bm. And difference because of the difference of output and input. Let's move on to next slide and further explore this linear constant coefficient difference equation. We also call it LCCDE, linear constant coefficient difference equation. So we can represent many systems with the help of linear constant coefficient difference equation. Here we are talking about the accumulator. So everybody knows that the equation for accumulator is this. So we know that in linear constant coefficient difference equation, we have just output and input terms. Okay, we have the delays of the output and we have delays at the input, and we do have some coefficients. So obviously it is not easy to convert any system into difference equation. Obviously once we have Z transform, we can easily convert it. But for now, just see how we can convert this system. So we know that if the sum goes to n minus 1, if the sum goes to n minus 1, we will have y of n minus 1 here. Okay, so one term is this, and the second thing that we can do is, if I separate the last term, from here, we know that the last term will be x of n. So if I write x of n separately, the sum will goes to n minus 1. So if we know that this and this is equal, so just substitute y of n minus 1 here. So in next slide you can see that the accumulator system in the form of difference equation is what? Current adding with all the previous output. Okay, so this is our difference equation for what? This is our difference equation for accumulator system. So if I rearrange, if I put all the outputs on one side and input on the other side, so we can note that the coefficient B naught here will be 1. Here the coefficient A naught is 1 and A1 is minus 1. So you have to compare this with general equation. Compare this with general difference equation, which is in previous slides. Okay, so this is the recursive block diagram of this equation. So you can see we have input is adding with output previous delay. So if this is output, if we use delay, this is y of n minus 1. Y of n minus 1 is adding with these two gets add and they will produce output. You have to do example 2.15 yourself. Okay, so we have compared the coefficient. These are coefficient. The order of input is 0, the order of output is 1. Let's move on to next slide. This is the recursive computation of difference equations. So here we have the difference equation satisfied by the input and outputs of a system. So this is a system that is given to us, which is in difference equation form. This is input, that is output, delay, and it is being multiplied with A, and here we have overall output. So what we can do, we can consider the input. This is given to us like the input is k into delta n, where k is an arbitrary number. So it means that we have system here and we have input this and we want to find out the output. So what we can do, obviously we have to specify the values to n. We know that output will be 0. Output y of n will be 0. Oh sorry, just let me clear for you. Output is equal to 0 for n less than 0. If I put n minus 1, the output will be 0. Okay, because this input will be start only at this input, because you know that delta of n start producing output only at 0. So if I choose n to be less than 0, there will be no output because the input is 0. So we have to start. Let me rub it for you and then tell you, like, so if we start beginning with this value, the output for n greater than minus 1, so we can find out the value greater than minus 1. This condition is given to us, the starting condition, that y of minus 1 is c. Before that there is nothing. So if I put n is equal to 0, y of 0 is equal to a, and 0 minus 1 will be y of 0 minus 1 will be y of minus 1, and we know that the value of minus 1 is c, so ac plus k. Now for next y of 1, a y of 0 plus x of n. We know that at 1, delta of 1, this is 0, okay, because x of n is equal to what? K delta of n. So if n is 1, so delta of n is 0, so it will be 0. So y of 0 will come from here, so we'll have this equation. So keep on putting. Next time we will put y1 here, so this is recursive. So the overall output will become this thing, comparing this a2, a3, a4. So we can see that the output will be a raised power n plus 1, c is constant c, then this a n, because for 1 it is 1, for 2 this is 2, so this n and this n, and then finally we have k. So the output for n less greater than or equal to 0 will be this. So this is recursive difference equation computation. Like, we are given with difference equation, you are given with input. You have to substitute the input in the difference equation and you have to find out the output. Okay, so let's move on to final slide of today's lecture. Now if you want to determine the output for n less than 0, you can express the difference equation like this. This is the same equation, we just have simplified it. Okay, we just have simplified it. You can either express this like this or you can express it like this. Okay, both are equal. This and this both are equal. So everybody knows the auxiliary equation that y of minus 1 is c. We can compute y of n for n less than minus 1. Okay, so here we can compute for n less than minus 1. Okay, you need to use this equation or this equation. So if I put, we already know what is y of minus 1, so we can start from minus 2. So minus 2, here is power minus 1, y of this, if you put minus 2 here, this will become y minus 1, and this is x of minus 1. So we know that input for minus 1 is 0, so the output will be a inverse c. So a inverse and y of minus 1 is c. So this is 0, this is 0, this is 0. Okay, so again y of minus 2, we have y of minus 2 computed here. So this is a minus 1 and then this minus 1. So this will become this a raised power minus 2 c. So if I look at these terms, so I can generalize it. For minus 2 it is minus 1. Okay, so 1 less. So I can say that for n less than minus 1, if there is n here, it means if we have minus 2 here, this must be minus 2 plus 1. So n plus 1, and then we have c constant here. So in sum, combining, if we combine the overall result will be, this is for positive n, this is for, sorry, this is for positive n, this is for negative n, and this is overall for all n. Okay, so here we have output defined for n negative and n positive. So this is recursive computation. I mistakenly told you in previous slide that the output will be 0 for n less than 0. I told you because when the input is delta impulse, so delta impulse is only defined for 0. It means that when you compute the output, the input roll will be 0. So x of minus 1 0, x of minus 2 0, x of minus 3, x of minus, and so on, and finally we are generalizing it. So that was it for today. I hope you got it. Thank you very much.